But our next presenter, I'd like to introduce Thomas Wade. He's Vancouver-based geophysical data processor with Geotech. He's spent the 8 years since obtaining his bachelor's in science degree from SFU, leading airborne geophysical surveys for AeroQuest and Geotech around the globe, and is an expert in the acquisition and processing of time-domain EM, ZTEM, magnetic, and radiometric airborne data. Please help me welcoming Thomas Wade.
So I'll be going over some test results of an integrated helicopter ZTEM-Gravity-magnetic. Gravity-magnetic system over the Vredefort Dome structure in South Africa.
Can't hear ya.
Sorry. I'd like to also acknowledge my co-authors Jean Legault, Jeff Plastow, Carlso, Izarra, and Latrous from Geotech in Aurora. So just to give a quick outline, I'll go over the background of the ZTEM instrument and then introduce the Heli ZTEM gravity-magnetic system. Then I'll talk a bit about the Vredefort Dome structure itself, show the results, some of the data that we collected, and then the 3D inversion results before concluding. So this slide presents the basic ZTEM system parameters on the left, the governing AF-mag tipper field equation on the top right, and the basics of EM induction measurements by the ZTEM system in the image in the bottom right. Notably that there's an E field directed into a conductor, causes a toroidal H field that circulates around it and creates a crossover type anomaly over top. The simple takeaway is that the ZTEM is a deep penetrating AEM method, and it relies on its airborne HZ receiver and its ground base station H to measure HX and HY. So the signal in AF-mag or ZTEM is the spheric noise in other EM systems. The current version of ZTEM AF-mag extracts the frequencies between 22 and 2800 hertz. The usable frequencies tend to be in the range of 30 to 720 hertz or 25 to 600 depending on where in the world you are. We found generally below 20 hertz they're quite unstable, and above 800 hertz we just don't have the signal strength reliability around the world. In spite of this limited frequency range, in general the ZTEM is a very favorable 30 to 3,000 meter depth penetration, which makes it an ideal depth penetrating geological mapping tool. So this slide illustrates the crossover type anomaly that we get with buried conductor in both the in-phase and the quadrature transfer functions for the inline or the X component in either the 2D or the 3D case. For a good conductor, that's the top left with high conductance or high contrast. The in-phase and quadrature signatures are usually very similar, but in the case of a poor conductor on the top right, the sign of the quadrature can cross over, can differ from the in-phase, and this is the reason why we measure both the in-phase and the quad components. In the case of a topographic feature on the bottom, we can also generate an EM signal. Oops, just go back here. Could also generate an EM signal that can be mistaken for an anomaly, or a bedrock conductor over a topo high, or a bedrock resistor over a topo low. So we correct for this in 2D inversions and 3D inversions. Most of you will be familiar with how the ZTEM system works in general, but I'll go over it here. This slide illustrates the basic helicopter ZTEM system. It was first introduced in 2006. Aside from the base station receivers and our data processing firmware, the system itself has changed very little since 2006. The main points are that the helicopter system still uses the large 7.2 meter diameter towed bird. And it's towed approximately 75 meters below the aircraft, weighs about 450 kilos. We generally get production numbers of 150 to 600 kilometers a day. So it's a pretty efficient 1 kilometer producer. We've flown a lot of ZTEM in the past, up to about almost 400,000 1 kilometers so far, worldwide. Its primary use is porphyry copper exploration, but especially in Canada we do a lot of unconformity uranium related exploration. some epithermal gold, and geothermal. This is the fixed-wing implementation of ZTEM that we introduced in 2011. It features an entirely redesigned ZTEM towed bird receiver. So rather than the helicopter system that essentially is dead weight, sling load, this one is essentially designed to fly. It's retracted from our Cessna Grand Caravan aircraft. Its aerodynamic design and reduced weight, it's about 50% less than the heli ZTEM receiver, allows it to be flown at a greater speed, generally 50% more. So we get an improvement in our daily line kilometer production of 350 to 750 kilometers a day. The onboard cesium magnetometer has been moved, so on the helicopter system it's on a towed bird on the tow cable. On the fixed wing system it's actually inside the ZTEM bird itself. So that improves the noise of the magnetometer readings, and because it's not close to the aircraft we don't need to compensate the mag readings at all. So here we are introducing our new integrated helicopter ZTEM-Gravity-magnetic system that was implemented February of this year. The system features an onboard GT2A airborne gravimeter and also deploys the ZTEM towed bird EM receiver and integrated cesium magnetometer as a sling load. So the 350 kilogram combined weight allows all three sensors to be flown using a standard A-Star B3 aircraft, pretty standard around the world. The fixed-wing bird's aerodynamic design and its reduced weight allows it to be flown at a greater speed, generally 30% faster than we normally would fly with a ZTEM system. And this is also contributed by, since we're flying a gravimeter, we don't contour the terrain. So we're flying directly over top of everything, we can increase the speed. Just showing the installation of the integrated system in our hangars in Johannesburg. So here's the towed bird next to a B3. The Geotech digital acquisition system slots in right behind the pilot seat. Behind the co-pilot seat is the GT2A gravimeter on its little spin table. And then here's a close-up of the ZTEM-Mag towed bird. To go over the Vredefort Dome itself, it's a complex impact structure with a diameter of about 80 kilometers, located in the Catfall Craton, about 120 kilometers southwest of Johannesburg, South Africa. It's the result of a large meteorite impact about 2.02 billion years ago. The central dome's 40-kilometer wide core is comprised of high-grade mid-Archean migmatitic gneiss of 3.1 to 3.2 billion years, from 25 to 36 kilometers thick. Phanerozoic sediments and dolerite sills, so it's the blue and the purple here, obscure the dome to the south and the southeast. The heli ZTEM-Grav-Mag lines that we tested are overlaying over top. So there have been many geophysical surveys conducted over the Vredefort Dome to characterize its geological features. These include, in 1990, Green and Chetty described the density of the core area by seismic refraction. In 2002, Henkel and Reinhold investigated the magnetic anomaly below the dome for thermal overprint from the impact event. And there have been previous airborne gravity surveys as well by Cowan and Cooper presented airborne gravity, as well as there's a Falcon AGG data set over the area. But with the exception of a Samtex deep crustal imaging program using broadband MT that were described by Mueller et al. In 2005, there's very little information on the near surface, or the upper 2-kilometer resistivity of the Vredefort region. In addition to the South Africa Council for Geosciences Ground Gravity Network and the recently published Falcon AGG results, airborne gravity surveys have been flown over the Vredefort crater, as I said, including fixed-wing gravity using the GT1A and GT2A system manufactured by Canadian Microgravity in Aurora. The fixed-wing GT2A survey also included radiometrics and aeromagnetics. The radiometric total counts and the TMI from that survey are shown. And their free air compared very well with the CGSA's data when it was upward continued to their level. So this slide presents the Geotech integrated helicopter system results over the Vredefort structure flown this year, February. The system test was flown over the northwest side of the Vredefort Dome, near the towns of Vredefort, Pontchartrain, and Paris. We flew 9 70-kilometer-long lines flown at 1 kilometer spacing, oriented azimuth 135, and 5 20-kilometer-long tie lines at 10-kilometer spacing, so a total of 450 kilometers. The GT2A airborne barometer was installed in a helicopter, as I showed, with the ZTEM and cesium magnetometer towed bird, and that was flown 82 meters below the helicopter. We selected a fixed survey height above all terrain at 1825 meters above the geoid, and that minimized the effects of vertical movement on the gravimeter. The ZTEM sensor was thus flown between 110 and 420 meters above the ground. Without the need to contour the terrain, the survey speed was increased to 130 kilometers an hour, and we experienced similar helicopter endurance and flight length that we usually see with ZTEM surveys. We completed the test in 3 days. So this slide shows the results of gravity repeat testing over line 1040 in the center of our test area. We did 4 passes to demonstrate the repeatability of the gravity measurements when installed with the ZTEM system. 150 seconds Kalman filter was applied to counteract aircraft movement and turbulence, so that equates to about 3,500 meters in length. And analysis of the overlapping profiles of each pass indicates an average RMS error between the repeat passes was 0.70 milligauss. So it's pretty close to the 0.6 that Canadian Microgravity measured with their GT2A and a fixed-wing platform. In this slide, we have obtained the ground Bouguer gravity data from the South African regional grid. It has a 1 kilometer cell size, and windowed it to our Vredefort test area here in the upper right. We've upward continued the Bouguer gravity to our average flight height of 1830 meters and removed a first order regional trend. And then we're showing here our results, Bouguer gravity results with the first order trend removed. And we see that they are identical in range, so 22.8 milligauss, and between the two have a 2.32 milligal RMS difference in absolute amplitude. So this slide shows the test results over the known geology. The airborne gravity and aeromagnetic data show excellent correlation with previously acquired data over the Vredefort structure. The gravity and magnetic highs in the central area, as well as the ring-like structures that extend outward. The ZTEM tipper data at high and low frequencies give a sense of the relative depth of investigation as per EM skin depth rules. So we have high frequency data on the lower left and lower frequency data on the lower right. In spite of topographic artifacts, the differences in the 2 TPR signatures are pretty clearly noticeable. So we have high frequency or shallow depth ZTEM results are low amplitude, which reflects a lack of lateral resistivity in the near surface. But our low frequency tipper data displays strong tipper response, which indicates a strong lateral resistivity variation at greater depth. So the higher relative conductivities near the center and also at the northwest edges correspond to the mapped Karoo and Transvaal sediments. This view shows the ZTEM 37 hertz total phase rotated data on the bottom over the digital topography from satellite SRTM, or I guess the shuttle mission. The similar but not always direct correlation indicates that the ZTEM response is induced by geology, not topography. The ZTEM also shows similarities with both the magnetic and gravity results, and that are mapping geology. We also noticed a very strong negative magnetic response that corresponds to the Witwatersrand outer granite contact and is clearly due to magnetic remnants. So this slide shows the inversion results for all 3 measured parameters. The 3D inversion of airborne gravity and airborne magnetics used the Geosoft MVI 3D inversion code. The ZTEM 2D inversion used Geotech AV 2D topo code and UBC 3D ZTEM inversion code. The corresponding 3D density and 2D, 3D resistivity depth slices at 500 meters, 500 meter elevation, show similar agreement with the observed data and the known geology. The 3D magnetic susceptibility model indicates an anomalous high at the Witwatersrand outer granite contact. So that's here. And where there was a previously low magnetic intensity indicated, confirming a negative magnetic remnants. The ZTEM 3D resistivity displays higher resolution relative to the 2D, but it also has a lower resistivity range, so 2 decades for the 3D compared to 3 for the 2D. And that's due to errors from the larger cell sizes in the 3D. This slide compares the multi-parameter cross-sections across the central line. Again, this is line 1040 with a sort of cartoon representation of the known geology. And this focuses on the 3D ZTEM inversion results. The 3D inversion appears to delineate a geological contact wall between the Witwatersrand strata and the Vredefort volcanics on this side. And as well as the amphibulite granulate transition sort of here. And we also marked the shear zone between the Caribou sediments and the granite fells. There are some artifacts from poor data fits in the 3D inversion. We got more than 25% error for convergence. That's because of our wide line spacing of 1 kilometer. So focusing on the 3D gravity inversion results, they appear to mainly map lateral contrast versus vertical changes, as you'd expect. The gravity is responding well to the main lithological unit contacts. The Caribou sediments are consistently low in density, whereas the Vredefort and Witwatersrand over here groups are shown in mainly higher density. Focusing on the 3D magnetic inversion results at the bottom, the magnetic susceptibility model is dominated by a central high located at the contact between the Witwatersrand and outer granite gneiss units. There's a magnetic high feature at depth below the transfer unit as well, on the far left. And the Caribou sediments and the Vredefort appear to be non-magnetic in this section. So to conclude, we did a survey test conducted with our new helicopter gravity-magnetic ZTEM system over the Vredefort Dome structure in South Africa. The plane wave EM fields measured by the ZTEM system make it relatively insensitive to flying height relative to other active source heli-EM systems. So it makes it an ideal pairing for airborne gravity measurements acquired at a fixed altitude. The ZTEM combination with magnetics also makes for a very low noise AEM platform for magnetic data. We don't need to compensate data, nor do we need to sort of apply any tilt corrections. The test results demonstrate that good quality, so plus or minus 0.7 milligal, very similar to Canadian microgravity's results. Airborne gravity measurements can be made concurrently with ZTEM and magnetics, and this provides a potentially useful multi-parameter and deep penetrating geophysical mapping tool. Future work should include integration with other airborne and ground data sets and include joint inversion with MT, hopefully for improved near surface resolution. So, thank you. We'd like to also thank the Carlso.
Perfect. Lots of time here. Questions?
Thomas, how many gravity systems do you guys have, and where are they?
We have one in South Africa and one in Australia at this moment. Both two.
And they're both flying commercially now?
Rarely, I'll say.
Well,
Yeah. I mean, obviously the market now is mostly for gravity gravimetry. There's nothing really on the horizon for us without the helicopter system.
How long does it take for you to move that system to a new location? Like if you wanted to get it back to Canada?
Pretty quickly, actually.
Okay.
The ZTEM systems are all sort of modular tubes, so they can be packed up into a crate and shipped within 24 hours.
Yeah.
Is there, setting the gravity side, you seem to have a configuration now for the standard helicopter ZTEM that will be faster and cheaper because it's a lower weight. You know, you can more fuel available for flight.
Yeah.
Is that something you're discussing internally or discussing with clients?
It's something we definitely have to test, this new fixed wing receiver on the helicopter. Generally, because of the lower weight, there will be obviously fuel savings, but we haven't tested how much the lighter system sort of tilts and spins when, say, climbing over mountains. So typically with the ZTEM survey in terrain, we don't have a perimeter on board. We do a loose straight over the terrain, so you're kind of contouring a little bit, and we don't have all of the data yet about how this system responds to that kind of punishment. So for the meantime, I would say the larger, heavier system is probably going to produce maybe better data in those conditions. But if it's flat, then yeah, well, I think we'll start deploying the fixed wing system with the helicopter.
And you're still using the same type of base station?
We've actually improved the base stations considerably. So they used to be, like a story tall and require helicopter transport in and out of the areas. Now we have what we're calling our compact base stations, which are essentially an 8-foot long tube that can be put on the back of a pickup truck. So there's some helicopter time savings there now.
What spec are you quoting in terms of the wavelength of the gravity that you can resolve?
That, I'm not sure. I mean, we do apply a longer filter, 150 seconds versus what would be standard 100 seconds for a fixed wing system, simply because a helicopter is much more turbulent. So that would have to look into.
Can you comment on the cost? Like, how much more would this cost than a ZTEM survey?
I think the cost would be borne out almost all on the processing side, because you get essentially the same production rate as a normal ZTEM survey. So if you have an area that is relatively flat, or you're flying with a gravimeter at a fixed altitude, the actual production cost would be fairly similar.
So 150%?
I don't know, I'm not on the sales side, so you pass your Sean on that.
Everyone heard that, right?
Yeah.
Any other questions? All right. Well, thank you, Thomas.